We're going to go ahead and get this started. Welcome to Build It. Let's see, I got a few giveaways. Who here is familiar with Security University?
All right, I'll bring it.
They're giving away a few free classes. Anybody interested? There you go. You have to turn these in at the booth. Enjoy.
I want one of those. Why do you get one? You're just a talker. You don't get shit.
Oh.
It's interesting.
I also got a few more things.
We should keep like track of some sort of.
Can I throw one?
You can?
Yes. You want to throw one? No, just throw it.
All right. Also got a T-shirt from last year.
That's what that means for. It doesn't have a time. Okay.
Oh.
We're breaking this off like a couple times.
Dead spot. All right.
Do we haven't actually practiced it?
I also have some few party details for tonight. Is everybody going to the party? All right. Party's going to start at 9 o'clock in the International Ballroom Center, or the Bring It On room. The entrance is going to be on this side. Everybody is required to wear a badge to get in. If you want to stay in the party, you're required to keep the badge on. There will be a selection of beer, wine, and soft drinks, and they'll be free up until midnight. Let's see. As you get to the party, there'll be a ticket that will allow you to get a mixed drink, and
Free beer till midnight.
you do. And it looks like it's gonna close up around 1 o'clock. We also have. Is everybody interested in some bags of M&Ms? I'm gonna try throwing these. Hopefully they don't break open. Oh. There you go. Enjoy. Share the stuff here. And then our
It's only 2:01.
talk is going to be on augmenting binary analysis with Python and Pin. It's given by Omar Ahmed and Tyler Bowen. Go ahead, take it.
Thanks. Awesome. So, how's everybody doing today? We're having a good time at ShmooCon. Everybody's having fun. Hope you're not too hungover from yesterday. But there's a lot of great talks that came before us. I really appreciate everybody coming out to see some of the work we've been doing. We put a lot of hard work and effort in this. I hope you guys can see some of what we've been doing and get a little bit out of it. Maybe learn a thing or two. I know it's kind of a crazy idea, but we'll see how it goes. So who are we? I am Tyler. I study at NYU. I'm a security researcher at Silver Sky. And
I'm Omar. I recently graduated at NYU as well. I'm a security engineer at Etsy, and here I am.
Right.
So what is binary analysis? We're really excited to talk about PIN, but before we can do that, we need to talk about binary analysis. So a binary, it's basically a file on disk that contains all the resources needed for a program to run. So this includes code, this includes any hard-coded strings, all sorts of things like that. So binary analysis is kind of like you're an investigator at a crime scene. You don't know what went on, but it's your job to piece together what happened. You want to expend the least amount of resources to get the job done, and it's very similar to a crime scene in that you've got native code. It doesn't tell you exactly what the developer's intentions were, but it's your job to figure that out. So one way to analyze binaries is using a debugger. So here we've got a really popular debugger, WinDebug. You can see, you can do all sorts of things like inspect code. So if you see the red line, that's where a breakpoint was placed. That's where the program will continue executing until it hits that. We've also got a call stack, so you can see which function did we call to get to this point, and you can also see the registers. It's essential to gain insight into how a program runs. A really easy way is just simply observing the execution of a binary. So this is the CMU bomb lab, which is used to train people for reverse engineering. As you can see, when you bang the keyboard, the bomb blows up. But when you do a little more educated guessing, you can see that the bomb actually doesn't blow up and lets you keep going. So this is just typing things and watching and seeing what happens. Another way is reading disassembly output. You're still reading native code assembly and piecing together what any of this means, but IDA, for example, makes things a lot easier by syntax hiding the assembly code, and graphing the flow for you so it's easy to follow with your eyes and just makes your life a little bit easier. A really easy way to do is running strings on a binary. So what strings does is it extracts all ASCII strings from a binary and prints them out. So this is a CTF challenge from one of the recent CTFs we played. When I ran strings on it, a few things popped out at me. So you can see I've highlighted, for example, libcrypto.so. You know that, hey, this binary, it probably does some cryptography. I might want to avoid it. It's got AES in there, more crypto. Encrypt, final, more crypto, and then you see socket and stir copy. So stir copy might raise some alarms for you if you're working on a exploitable service, and socket is a clear indicator of network functionality. And we figured all this out without even running it, without reading any code, without looking at anything fancy.
All right, so basically what he's talking about here can really be broken down to a couple different categories, mainly two. We have static analysis, which is reading assembly, running strings. On program, this is obviously a very popular technique. It's probably the most popular technique, and you can get a lot out of it, but it also costs a lot of resources and a lot of your time. It also has a higher barrier of entry. Reading disassembly is not easy. You have to understand assembly, which is obviously hard. So that's the one option. Our second option is dynamic analysis. You can use a debugger. You can run strace. You can do all these things very easily, and you can gain insight into a program really, really quickly, and with extremely low barrier of entry. So it's important to make a distinction where both are applicable, but used hand in hand, they can be more beneficial than by themselves. So static versus dynamic with speed. Another cool thing about static analysis versus dynamic analysis is static, you can get a full 100% code coverage. There's certain passive code, like we saw in Inner Explorer with the recent unicorn bug, right? That bug has been around since like 1995. There's parts of that code that simply don't get touched all the time. If you're doing static analysis, you can make sure you look at all of the code, whereas dynamic analysis, you're definitely going to miss bits and pieces, but it's all about your end goals and your what you're trying to accomplish. So with that being said, that brings up dynamic binary instrumentation.
So dynamic binary instrumentation, it's just a fancy way of saying you're modifying code before it runs based on certain conditions. So this might include injecting code, this might include modifying the code. So for example, a really common way for debuggers is to insert an int3 instruction on x86. So what this does is when the int3 instruction is executed, the debugger gets a signal, and this way it can defer to the user. Say, the debugger can be like, hey, user, now what do you want to do? This program is at this point ready for you to inspect. So a really easy way to get started with dynamic binary instrumentation is debugger scripting. So there's GDB and LDB. You can use Python. You can use GDB scripts. WinDebug, we saw it earlier. You can script it using Python, but unfortunately it's Windows only. And you've got VDB, which is pretty cool because it's pure Python. Works on Windows, OS X, and Linux. Yep. So here's an example of a debugger script that I wrote for a CTF challenge. So for those who aren't familiar with linked lists, it's basically you've got several nodes that point to each other. So you've got node A, node B, and node C. Node A's next points to B. Node B's next points to C, and C's previous points to B, and B's previous points to A. So this is something that's written in native code, and you might not want to read any of that when you're working with the program. So this script just makes your life easier because it attaches to the program as it's executing, and now you can insert debug statements, which is something you would require a source to insert debug statements. You would need to recompile and all of that, but with debugger scripting, we were able to print out the name, the value, next, and previous without having to write any C or whatever the program was originally written in. This is important because now you can get some insight into the program that the developer didn't want you to have, and it becomes easier to spot, for example, a bug that may trash the linked list or anything else once you realize your script is behaving weird. Another popular framework is Valgrind. It was initially designed for developers to basically have better coding practices. It catches all sorts of things like memory issues and performance issues, all sorts of things like that. The cool thing is it works on many popular platforms, even BSD, which most DBI frameworks don't support. So how Valgrind works is that it translates your assembly code before it runs into something called VexIR. It's an intermediate representation that just makes the assembly easier to understand for Valgrind, and it also makes Valgrind more portable because it can translate numerous architectures into a single representation, and that representation can be used anywhere. And then you've got this instrumentation framework where you can write on top of it, and when you write on top of it, you can interface with the framework, and this framework lets you perform transformations on the IR. You can do, you can inject code, you can instrument code, you can do whatever you want, and then once your tool is finished running, it translates it back into the host native assembly language. So you go from x86 to VexIR back to x86 on x86.
So Valgrind's pretty cool, does some good stuff, but one of the biggest problems with Valgrind is it's really slow, and you can't do large instrumentation for long periods of time. Oh, I killed it. I killed it all. Anyway, technical issues, right? This works. All's well in the world? No? Okay, all's well in the world. Awesome. So Valgrind's slow, and it's really good at what it does, but the Vex intermediate language is very difficult to write. It's very difficult to prototype. So the Google Chrome security team came out with this cool tool called Address Sanitizer. They call it a fast memory error detector. It basically can detect use after freeze, heap overflows, stack-based buffer overflows. The way it does all this is it actually recompiles the program. So that takes out, that brings in another problem we have here. What if you don't have source code? We're trying to do reverse engineering, trying to do things of that nature. Address Sanitizer may not be the best choice for you, but it's really good as like a crash test harness for fuzzing. Like that's kind of what it's best known for. Is it's not very cumbersome on the program. So you can run this and do a lot of fuzzing, and you can detect your use after freeze and things of that nature with this program. So the way it does this, like I said, it recompiles the program. So what it does is it maps all of the program's memory into a second heap that it keeps track of called shadow memory. Every 8 bytes of memory in the program is mapped to 1 byte of memory in the shadow heap, and they just use simple integers as seen here. So if it's all unpoisoned data, that means it's malloc, it's ready to use. The user's fine to use it. You can just throw a 0. If it's not, if it's freed out, you throw a negative value. If it's only partially in use, they use the partial data there. So with the recompilation, they actually replace the malloc and free functions out of the binary and replace them with their own variation, and that's how it's able to do this so quickly, efficiently, and easily. So here's just a little picture showing what it looks like when Address Sanitizer finds a crash. It gives you this nice little dump out, showing you these FAs saying that there's a problem there. And so Address Sanitizers are so popular these days that even Mozilla Firefox and Chromium, they come with open builds with Address Sanitizers built in just for testers and things of that nature. So while our talk is on Pin, it's on Python, all that stuff, Address Sanitizer is a really cool tool, and I think that most security people should at least check it out, at least see what it's up to. It's really, really awesome, and it's been really welcomed by the open source community. So I think it's definitely something cool to check out. So is this me or you? Is this me still? Okay. So with that being said, Valgrind's cool because it allows you to write custom tools, right? But nobody wants to write custom tools in a weird intermediate language that they don't necessarily understand. So what people have come up with is another kind of framework that's very similar to Valgrind, but it lets you write tools in a language you're more familiar with. Namely, C++ is the choice for most people. One such framework is called DynamoRio. It is a code manipulation system that actually is able to inject your code into a binary. So you can, it's very similar to debug hooking. You can write a program to analyze this binary in C++ in a language you understand, and actually get that code to be executed in the program's interface, in the binary you're looking at's interface. So DynamoRio is awesome. It's cool. It's open source. It kind of works for Windows once in a while, maybe. If you have GDB and you have a very special build, you can sometimes get DynamoRio to work, but it's a little bit more cumbersome. The documentation on it is not as great, and it is a direct competitor to the choice that we use as Pin. Pin is a little bit more popular, so that's kind of why we got more introduced to it, and that's one of the reasons why we chose to use it over DynamoRio. But DynamoRio is really cool. I recommend checking it out. So what is Pin? Again, it's very similar. It allows you to insert arbitrary code into an executable to do more thorough analysis. You can do a lot of checking of and a lot of hooking, checking, all that sort of good stuff with pin. Right. So pin is the framework, and the tools you write in C++ are pin tools. That was a key we wanted to get through here. That you write these tools. Pin injects your tool on your behalf, and your pin tool is like the hook that does that. The pin is like the debugger hook, and the pin tool is like the debugger hook, and pin is the framework that sticks it in.
So why pin? We've been here talking about pin, and we still haven't told you why we prefer pin to everything else. So first of all, pin's got really amazing documentation. If you're ever lost, it's surprising that the developer docs that come with the program actually help you. I found that pin's documentation is basically all you need. The same exact API works for Windows and Unix, so if you write a really cool tool on Linux, you can port it over to Windows with very minimal work. That's because pin, the framework, it abstracts away a lot from the operating system, so to the point where you don't need to worry about it. So for example, if you want to know the syscalls that are currently executing, you don't need to specify, you don't need to know anything about syscall numbers, you don't need to know any syscall names, you don't need to worry about the version of Windows you're running. Pin takes care of all that for you. It's also extremely popular, so you can just search GitHub for pin tools, and there's just so many of them. Everyone uses it. We play CTFs a lot. We've read a lot of CTF write-ups that use pin. We've used pin for CTFs in the past ourselves, and we just really like it. And the best of all, nothing needs to be recompiled to be used with pin. So if you've got a program, you don't know what it does, you don't have the source code to it, you don't need that. So like with address sanitizer, we saw while it's a really great, amazing tool, super powerful and all that, you need the source code. With pin, it just injects code as it runs, so we don't need anything. It's really easy to get started with pin as well. So when you download pin, it comes with around like 20 pin tools that can do all sorts of crazy things. If there's something you really want to do and you're not sure where to begin, there's probably a pin tool that's included with it that includes some of the functionality you need. So you could actually get really far just by copying and pasting pieces from different default pin tools. Like I said earlier, the documentation is really easy to follow, so as a newcomer to pin, you're not going to have a hard time. And of course, installation is a piece of cake. It's closed source, so you just get a bunch of binaries and you just literally download and run. Yeah. So the cool thing about pin is that it can be as granular as you need it to be. So as we saw with the debugger, you can break on function calls. Well, pin lets you do the same exact thing, but you can go even lower than that. You can go to the basic block level, or even lower than that, you can go to the instructions. When you look at instructions, pin gives you access to, like for example on x86, you can look at the E-flags register, you can look at all sorts of registers, which sometimes isn't as easy to do with a debugger. You can hook all sorts of things. There's more than just these three things, but ultimately it just comes down to personal preference.
All right, so why not pin? No, nobody really likes to write C++. Okay, there's a rare person on occasion that likes C++, but pin C++, which I'll show you in a couple minutes, is even worse. Like there's type defs for everything. So if you want to do anything, so instead of using an unsigned int or an unsigned long, you'll use this adder int. That's what we use for everything. And then eventually writing a pin often enough, you get used to it, but it's really cumbersome at first. So you're writing with all these weird types, weird to deal with. It's hard to prototype. One of the reasons that Python's popularity has gone up is because you don't type make every time. I don't know why people are so lazy, but typing make is like the crutch of C, right? So C++ has the exact same problem. Pin has the same problem. You have to type make every time. It's a pain. It's a little bit slower than our DBI frameworks. That being said, we can instrument a browser and see very minimal performance impacts. Even with our Python implementation, which is obviously Python a lot slower than C++, you're still seeing minimal impacts. So it is slower, but I don't really think that the average user would find that. It's also not as granular as other solutions. So if you're trying to do very advanced program analysis techniques like taint tracing, an intermediate representation can really help you. So that's where something like Vex from Valgrind might come in and be a little bit more helpful. But if you're doing something that low level, so pin might not be the best option for you. So we talked about pin a lot. We've only talked a little bit about what we were able to, what's been done or what's it been known for. So most notably, pins, I'm sure most people know about EMET from Microsoft. Well, the competition that got ROPGuard, the ROP catcher from there, the winner of that competition actually used this pin tool to detect ROP at runtime. And Microsoft ended up going with this choice because it's a little bit heavier, so they actually ended up writing their own custom implementation of it that they use in EMET now. But it's very similar to what pin does. Also, IDA Pro, after version 6.4, it comes with a pin debugger. So I guess we're kind of telling you these things just to show that the pin has a little more credibility than just what we've done with it, what people on GitHub do with it. It's actually used in the industry a lot. It's actually a really popular tool that can be used in a lot of different ways. So everybody's here, everybody likes to find bugs, right? 0 days are the big popular thing. What can pin help you find? Well, pin can then hook on any library functions or any system calls, so we can obviously trace out, easily trace out buffer overflows. We can trace out printf format string vulnerabilities. Even though those died a few years ago, we can still find them and maybe get memory leaks, something of that nature out of them. With use after freeze are the hot stuff for the past couple of years, right? And they can be difficult to find. They can be difficult to trace down. Pin can be used with a little bit of manipulation, a little bit of coercing. We can find use after freeze, and we can find overflows, and all that good stuff. So this is just we're going to go into this more in a few minutes. This is kind of just a quick little idea of how you check a heap out of this use after free, I think this is. All right, this is kind of not a good slide. Anyway, let's look at some pin. That slide probably should have gone on, by the way. All right, so anyway. Oh. I thought it was mirrored. All right, cool. So this is just a C++ pin thing. Oh, you have regular scroll. Yeah, as you can see, you can start seeing a little bit of odd types and such. So what this is doing is simply, we're going to go, let's bring back to the thing. Let me go over the algorithm real quick. This doesn't make any sense. Bring me back to the slide. Sorry, man. I talk about this algorithm in a second. It's probably better to talk about it right now. Cool. So a basic idea of how to do heap overflow protection and use after free protection that we came up with is similar to what address sanitizer is doing. What we're going to do is we're going to hook on all allocation functions. Every kind of allocation function that they have, malloc, calloc, realloc, and free. And what we're doing is if you make a canary, like a heap canary on it, you can then check that canary with all reads and writes. If you're reading and writing the heap, I can verify what value you're reading and writing to. If you're reading and writing to my canary, then obviously you are overwriting, you're not in the memory that you should be in. So with pin, this is actually really, really simple to do. You can easily adjust sizes with pointers, and it's very simple to be able to get this basic heap overflow protection. We'll go more over the user free stuff in a minute, but that's the general idea with the heap overflow. And then, I don't know how to use your computer. Cool. And then, so you can kind of see that we're doing some fun kind of. Cool. So like, you can just see that we're doing a little bit adjusting. You're modifying the size of the argument to malloc and adjusting it so that we have room for our guard pages. And then one of the little tricky implementations things we had, because the talk is today, not next week, is we actually don't free anything. So a problem with that was that, so you notice here, we just set free to 0, we set the whatever's passing the free to 0, so we don't actually free anything. So you can't use this long term, you're going to run out of memory. But the reason why we did this is because pin has the problem of the chicken and egg problem. What came first, the chicken or the egg, right? So pin has to load itself into memory at some point. So it can't hook on all mallocs and frees. So if something that pin got loaded into initially with gets freed, it's not going to have the guard page, and then my guard page is going to crash. So what we decided was, just for the demos, just for the test now, we're just not going to free anything. Obviously, you could make better choices here, but we were on a time crunch. But anyway, as you can see, the code is kind of a mess. There's a lot of weird things, weird dereferencing happening. It's not that messy, actually, it's not too bad. But, so this is kind of where we start doing some inserting the calls, and you have to use these weird pin type defs, constants, to pass in parameters and arguments and all that good stuff. And it's all really kind of confusing, and it takes a little while to get used to it. So when I look at it now, I feel comfortable with it, but we've been doing this for a couple months now. So it's very hard and cumbersome to get started with. So that's kind of one of the leading reasons why we started this Python pin idea. Bring me back to the slides, please. We have to go back a few. I jumped ahead, sorry. That was too many. Cool. So pin can do some really cool stuff, and it's really awesome. But much like C, I didn't do it, I didn't touch it. Much like C, much like C, it is a mess, right? So it's hard to write C programs. There's a reason why C is not as popular as it once was. There's a reason why Python is the #1 language for like beginners and people learning, because it's easy to use, it's easy to prototype, it's fast. Some might even say it's fun. It's a tough argument to make, but some people would make it. So C++ is nobody likes it. It's gross. Like I said, it's hard to prototype. You have to type make every time. A lot of extra minutes spent there. And it's also difficult to understand. It's hard for other people to read your code. It's really easy to write gross code, ugly code, insecure code. It's all reasons why we kind of decided that we wanted to make it a little bit easier and write a Python implementation. So, what did you say? Right. So we kind of just looked at this. So this is the C++ version again. What is this doing? It's saying it's finding malloc by name, as it says up there. And all it's doing is hooking on the malloc. It's hooking on the malloc before, and it's hooking on the malloc after. So that way you can look at what's passed in the malloc, which will be a size, and you can look at the address that it gets back. Again, this is cool for the little heap check thing I made, so that way I can actually modify the memory that's getting passed back and forth to the user. Again, you have all these weird constants, all this RTN stuff. It's kind of, it's a lot. And this is our, what? Your turn? This is still Tyler. And then,
okay, so as you can see, we're basically doing the same thing in Python. So we went from around maybe 100 lines of C++ to like 10 lines in Python. So what we did was we wrapped a lot of the pin functionality in Python. This, as you can see, it's a lot easier to read. You can see you've got your simple if statements, you've got your insert calls. It's all just one line. It's nothing too verbose. When you go back to C++, you've got all these strange constants. You've got these, like you've got cast. Like no one likes that. In Python, you don't need any of that. Python, more people are familiar with it anyway, so it's basically indented pseudocode, so it's a lot easier to read. So Python, simpler, cleaner. Best part is you don't need to type make if you want to use it. You don't need to recompile it every time, and extensive libraries. So you've got like you can use any module that you're used to using in Python. Now you can put them in pin. So whatever you like in Python, now you have it with pin. You can combine the two and do some crazy things. So how it works is that it's essentially just a Python interpreter embedded within the pin tool. So as you saw earlier, we have to write C++ for a pin tool. So what we did is, instead of writing the pin tool in C++, we wrote a Python wrapper in C++ and put that in the pin tool. So if you ever use GDB, for example, the Python extension for GDB, that module only exists within GDB. So when you do import GDB, that doesn't work outside of GDB. We're doing the same exact thing. So you've got a virtual pin module exposed to the Python script. So that's the pin module that we were using earlier. So it gives you access to most of pin's functionality. So when you saw earlier the RTN insert calls, the RTN close, all of that, that just went from C++ land to Python land. So it's basically easier transition for developers. You can also get seamless integration, like I mentioned earlier, with any modules you're comfortable with using. So like, for example, Z3Pi, if you're interested in symbolic execution, SMT solving, any of that, you can do Z3Pi and PIN. So you can do some crazy symbolic execution engine, anything you want. PIL, Python Imaging Library, is a really popular choice. With Python PIN and PIL, you can do some cool visualizations. For example, you can map out the heap based on, if you like hook malloc, you can graph it, and then you can render a JPEG out of it, and everyone likes fancy images. You can do SciPy, science map things with PIN. So there's a little diagram. You've got the PIN tool in the middle, which basically arbitrates the communication between your Python code and the PIN framework. The interpreter is within that PIN tool, and that's basically what handles everything. So,
let me take over for a second. All right, cool. So we talked about the heap checking thing here. Right, the basic picture, poison guards on both sides. That covers underflow, overflow. You can set the guard size yourself. I think mine's 32 bytes, so that covers a little bit. So obviously it doesn't protect everything, but it's a simple protection that helps a little bit. So the other thing is, I think I was supposed to tell you that use after free is when the allocation algorithm thinks that something is freed, but there's still a reference to it. So what can happen with that is they can reissue that memory. You have a reference to that memory, they reissue it as something else, and that can cause problems. You think you have one type, and it's actually something else. So attackers try to like kind of pull the rug out from underneath you and put some other code there, code that they control. So the problem with these bugs is they can go undetected for really long times. If the allocation algorithm does not replace this with something, it's not going to crash. Most of the time it's not going to crash. Most of the time you're not going to have any problems because, but a well-crafted attack can actually take advantage of these things. So it's been imperative of the past couple of years to try to figure out ways to detect these use after frees, and that's why address sanitizers become so kind of popular. But what we do here is we keep track of everything that's freed. So if PIN could hook on all free functions and you have to pass things to free, and I can tell you what you pass to free, I can just keep track of all these, right? And then I can kind of map out an address space in my program to tell what's freed and what's used. And because I'm not actually freeing anything, there's no possible way that the memory allocator can give it back to anybody. So once it's freed forever. Like again, this would not work for a large period of time over with large programs, but it does work for good testing and some good fuzzing testing and things of that nature. So all we do is we take anything that you pass to free, we keep it in our free list, and we map out a little address space. So we have a low address and we have a high address, and if you try to use something with a heap read or write, we can easily check if you're in that address space. If you're in that address space, we check if you're freed, and it's a relatively simple thing. So you can see this little diagram here: free list, allocated blocks. Limitations. So it's large computation time to check the free list every time. And we're doing this on every heap read and write as well. So you can kind of think in your mind there's a lot of heap reads and writes that happen in an average program. So this is obviously going to slow things down a little bit. We talked about the chicken egg problem already with the PIN thing. That's why we don't free anything. Awesome. So do you guys want to see code first or demo first? Any preference? Demo. Okay. We'll show the demo, then I'll show the code, and we'll talk about it more because I know it's really exciting to hear me talk. All right. So I guess we should show them the source code first. No, the source code for the demo program, so you can see the bug. Not just like real quick, just real quick. So we tried to make it kind of subtle. There's like a subtle off by one bug, right? Just take a second to spot it yourself. But we wanted to show that like an off by one thing is like one of the most common programming errors. Probably the most common programming error. I'm sure everybody's made it once or twice. And again, that's another bug that can go undetected for a while because nobody's actually going to, it doesn't necessarily, there's not really important stuff before or after your buffer. There's a potential that it's going to run and be just fine. So off by one is another cool, tricky problem. And so like I talked about before, with the canary pages, the guard pages, whatever you want to call them, we're able to check on reads and writes and be able to spot something as subtle as an off by 1 error with little to no extra overhead time running inside a pin. So just run the demo, I guess. So as you can see, it's inconspicuous, it's no problem, right? The program runs fine. So if you're fuzzing or testing on this, you would obviously call this a good case, that data is not bad, there's no problem with this program. You run it under our pin program, our little pin tool. I guess it kind of defeats the purpose of the funny joke about make taking a long time when you have to write it out so long. That's neither here nor there. Cool. So it just shows you that the heap overflow detected. It shows you where it happened, what the instruction was that it happened on. Then the third address to the right, not that one. God damn it. That's the instruction. Then after it says heap, that's the address it was trying to write to. And as you can see, the value is my little canary value. You probably should make that like a random value or something, but I just set it to 0f, 0f, 0f because I just finished that this morning, so it was like, it's hard. I had to like make something somewhat simple and easy to detect, but like a random value or something of that nature that people wouldn't be able to guess would probably be your best bet. But as you can see, inconspicuous program, small bug, subtle problem, and it's very easy to detect. The source code for this one? Is this the Python one or is this the C++ one? C++. Okay, cool. So yeah, we'll go through. This is C++? I thought it was Python. No. Oh, shit. Dude, do the Python. That was Python, I thought. I'm pretty sure it was Python. Do the Python one. Do the Python one. Okay, go to Python source code. Python source code. Python source code. All right, so that one was a C++ one. I thought it was Python. Cool. So like I said, I wrote that one in C++. A couple days ago, and this is the one I finished this morning. This is the C++, I mean the Python version of the same thing. This is actually an older version where the canary is 4.1, but I updated that. Oh, all this is on GitHub, by the way. We open sourced it like 10 minutes before we came here, so you guys should all check it out afterwards. We'll talk about that more in a minute. But anyway, so pin exposes a lot of functionality, exposes a lot of data to you, and we can't make our own structures in Python, we can't do that sort of thing, so the big, what people do for structures mostly is dictionaries. So we have really large dictionaries full of information, and that's what you're seeing here. So we have malloc before, and because, like I said, I finished this morning, so don't mind all the globals. Like I know that's bad coding practice, I'm sorry. But, right, we can get pointer. Okay, cool, so as you see, we actually abstract pointer setting as well, because like I was talking about, with my heap check thing, we're adding 64 bytes to every malloc allocation, and with that, we are then modifying the first 32 bytes and the last 32 bytes to have our canary value. There's really no way to do that if you don't have pointers. So we actually had to abstract away pointers with our Python implementation as well, so you can set and get arbitrary pointers through memory, but it's a little bit more cumbersome. Right, so you can modify registers, you can modify so it's all 64-bit, so the first argument's passed in and then the RDI register. Pin calls them GDI just for fun, just to be confusing. And yeah, so we get and set pointers off that. And then this really wonderful block of code, this is a really elegant code here. You can see we're adding values to it to write our canary value in properly. Yeah. And then again, we're making sure we're setting everything to 0 for the free, and we're adding things to our little free block. Yeah, and then the use after free checking stuff is probably the most interesting. Realloc after and realloc before are almost identical to malloc and free. It's pretty much the same thing. Cool. So this is a little bit older version that doesn't have. So all we're doing here is just checking if the x value is the canary value. The value of the heap. The value of the heap is actually stored in our little dictionary thing. So we store it in our dictionary, and we can check the canary value. Very easy, very simple. And then we also have our free list set up. And in Python, it's extremely simple. Just if this is in this list, do this. The problem with that is the fact that Python is really slow. And this implementation actually was a 40 or 50% timing, or 40 50 times time increase. So one of the ways to kind of combat that was you can, like I talked about earlier, we can map our memory address out, and you can do preliminary checks before you have to actually loop through the whole list in Python. So this is just the loading things, like we showed you before, and it's just a lot cleaner, a lot easier to see, a lot easier to use. And now, I know the amount of lines doesn't actually matter, right? If you have 300 lines, it's not a big deal versus 100. But the C++ version of this is close to 400 lines, and this version is only 100. So while the amount of lines is not a standard to measure by, it definitely is a lot easier and simpler to write 100 lines versus 400 to do almost the exact same thing. What do you want to do now? Do you want to run this one and see this? Because we didn't do that already? All right, let's do that. We'll run that guy for you. It's going to be the same output as before. Just show you our odd little syntax to run our Python pin tools. Sorry about the display being a little bit odd. You can blame the ShmooCon people at the party tonight. It's not a big deal. So while the syntax is a little odd and cumbersome, it is it's all documented on the GitHub page, so you can kind of get an idea of what you're doing, how you're doing it. It's heap_UAF. Yeah, that one. Cool. What the fuck? This is awful. Cool. Awesome. So, like I said, I pushed a couple updates that didn't seem to make it to the talk, unfortunately. But you saw the big slowdown, right? That was really slow, really slow. Like the use of the free detector is a lot faster now. But I don't know why. But unfortunately, we didn't get the updated version that I just pushed. But yeah, so it's kind of slow and kind of cumbersome. But it's doing the same thing. And one of the reasons we chose this demo versus some other demos is it kind of shows that you're doing a lot of low-level things here. We're doing a lot of we're doing actually directly writing to memory. A lot of things that Python is not known for, is not known to be good at, and a lot of reasons why something like this doesn't exist. Other versions of a similar tool do exist, but not to the full extent that we thought they should. And this is one of the big reasons. The writing to memory, being able to do those sorts of low-level things is not something Python is normally thought of, but we kind of wanted to show that it is possible, and it's not that terrible. Yeah.
Cool.
You could also do some of the basic demos too.
Yeah, so
simple examples.
A little simpler demo I'll be doing is socket instrumentation. So,
we got 15 minutes left just so far. Probably 10 minutes.
Okay, so normally when you want to spy on socket communication for a process, you would use a tool like TCP dump or Wireshark, but I find that to be a little heavy if you just want to see what's coming in and out. So I wrote this simple pin tool that all it does is it looks at receive, send, read and write for sockets. That's basically all the functions you'll need to worry about when you're looking at socket communication. There's also send and receive, but the binary that I'm looking at doesn't use those, so I didn't implement them, but it's not difficult to adapt them at all. So first I'll start the service. So this is a CTF challenge from some other CTF this year. What it does is it's running a network service, and I'm going to connect to it. Ignore that. Okay. So as soon as we connect, we're given a prompt. Let's just try messing around with the service. Okay, that's not a valid code. Let's try requesting something. Okay, so we're not getting anywhere with this, so I'm just going to exit. And then if you look at the outputs folder, basically you've got a bunch of text files containing the communication based on the process and the file descriptors. So let's look at just one of them. So basically this is everything that exited the process through the socket. It's all been logged to a file. As you can see, there's some leaked bytes here. This is part of the CTF challenge. It's meant to be a subtle info leak, but now we've got it leaked. There's also this other file descriptor. This is basically everything we entered. You can see this is pretty lightweight example, but it's a lot easier than TCP dump, for example. With TCP dump, you'd have to write to a PCAP file, and then you'd have to parse that PCAP file. With this pin tool, which is like, I'll show you the source code for.
You're good, man. You're good. We're on a long time. You're fine. We're on a long time.
Yeah. So literally all we're doing is we're looking at read and write. We're hooking the read before, we're hooking the write after, and then we can see literally all we want to do is just write it out to a file. This is 52 lines of Python to get basically the core functionality of TCP dump. And you get a lot more functionality because you can really easily extend it with Python. So yeah. I guess that's it, right?
Wait, no, go back to the slides. Talk more about Python pin itself. Negative, hey, hold it, hold it. No, we're not done yet. All right, cool. So, right, so Python pin, while it is done, the 32-bit support didn't quite get ported over properly. Somebody doesn't know the difference between longs and ints. It's not a big deal. Don't worry about it. He's a web guy. It's not his thing. We need to finish up. So it works for Mac and Windows, but the header files and things are a little bit odd. They're a little bit different. And so we're going to have to finish that up. We also tried to, Pin is really known for, it has tons of examples. It has tons of source code that you can play with. It comes with this huge library of things. Well, we only brought we probably made like 12 examples trying to emulate what they had. But we tried to make sure we had enough examples to encompass a lot of the functionality that we were able to do, and we made a couple more difficult examples so that when you look at it, you can kind of have an idea of what's happening. So I guess that's pretty much it. This is all open source on my GitHub. It's at the github.com/blankwall. If you look at my Twitter account, I posted it up. If you don't remember, you can just ask me later. It'll all be posted. These slides are posted. So our acknowledgements, these are people that helped us do things, some of the people that helped us get here and made this talk possible. And slides and pin tools we posted there. And then it's open for questions if anybody has any questions. If not, you can go early. Thank you all so much for being here. I hope you have a great day. See you at the party. Awesome. What's up?
You mentioned you acknowledged that Python is slow.
Right.
You were working on small challenge binaries. You guys done performance impact warning programs, and you consider rewriting some of the heavy stuff like C extensions?
Right. So the whole thing's kind of actually implemented like a big C extension, and that's totally true. So when we did stuff with like the pointers, that's all mostly really written as a C extension, and that's really the way that you have to go about it if you're trying to do really low stuff. So. But that's kind of really cool things is you can write parts of your program in C and other parts not in C, so it's helpful.